Hi, welcome back. We ended last week with some success and a promise of more challenges. We realized that no matter how much we'd added, we still had to make modifications to our little universe. We discovered the planets, we had to add them. We're going to see that they move too. We're still pretty much in pace with Aristotle, but we're going to take that little thread, these extra moving parts, and we're going to pull on it. And by the time we're done unraveling it or following the way scientists unraveled it, we will have gone places that Aristotle could not even have begun to imagine. And we're going to spend much of this week actually away from astronomy, talking about fundamental physics. It'll be tough, but I promise you it will pay off, because what we learn this week, what we bring up, the understanding we take away from it, is going to help us understand everything we talk about throughout the class, and hopefully way beyond this particular astronomy class. And of course, the father of all of this is Sir Isaac Newton. So let's start with the beginning. We'll start with the problem we found. And Aristotle would have been perfectly aware that there are 5 planets. Planets derived from the word for wandering, because these were very bright stars. The 5 were Mercury, Venus, Mars, Jupiter, and Saturn. And they, as we saw in our image, follow paths very near to the ecliptic. We're beginning to sense a pattern here. And they move along the ecliptic, so that means we need planetary spheres in addition to the lunar and solar and celestial spheres that we have. So far, so good. They move around the ecliptic at different rates. Each planet moves at a different rate, so certainly you can't put them all on a planetary sphere. You need a Venusian sphere separate from the Mercurian sphere. So we're up to 7 moving spheres and a celestial sphere. Their motion is not completely regular. Remember, even the sun doesn't completely move uniformly around the ecliptic, but the deviations for the planets are far more serious, and in fact will end up telling us something deep. So let's look closely at some of these deviations from regular motion that we see with planets but do not see with the sun and the moon. In the simulation, we're looking at a patch of sky near the constellation Gemini and Leo, just to the east of Orion that we were looking at before. And we see the ecliptic, and we're going to focus on the behavior of the planet Mars. And this simulation starts a little over a year ago in October 2011, and it's set up so that time advances by sidereal days, so that the stars repeat themselves. And we see that Mars, like all the objects that we've encountered so far, is moving slowly to the east along the ecliptic. We see the moon here moving much faster to the east along the ecliptic. And as time rolls by, the moon will quickly overtake Mars. But then, as the moon overtakes Mars, in December last year, something weird happens. Mars, in fact, stopped its eastward progress. And then, for about 3 months, Mars was actually moving west along the ecliptic. And then it recanted and continued its normal eastward motion. This retrograde motion of planets, and it happens for most planets, is a slightly more involved engineering challenge than what we've met so far. Challenging? For sure. It's not easy to construct a model that leads to the apparent motions of the planets in the sky as we see them, but very brilliant people were working on this, and they were very competent geometers. And they came up with a solution. This was first, the germ of the idea, first proposed in 150 BC by Aristarchus. And the basic idea is that to understand how Mars moves, you imagine that there is a circle around Earth called the different. And essentially, Mars moves along this different, but it's not on the different itself. On the different rolls an epicycle, which turns itself, and Mars is at a fixed point on this epicycle, so that as the animation runs, you see that the motion of Mars rather resembles what we saw in the picture. In the simulation, Mars is sometimes moving faster, sometimes slower, and sometimes even retrograde. And so, along these principles, by combining a different with an epicycle, one could describe the motions of the planets as we see them. Explaining how it is that sometimes a planet moves faster and sometimes slower is one thing, what we were after, or what they were after, was an actually precise matching of the predictions to the data. And this leads to a rather elaborate model that Ptolemy comes out with 300 years after Hipparchus floated the idea. For example, in order to understand why the sun does not move at a fixed rate around the celestial sphere, the solar sphere is a little bit off center. Its center is not exactly on the Earth. And there are various such elaborations. The end result is that the model is extremely successful. It makes good predictions far into the future about exactly where in the sky, where on the celestial sphere, you'll find which planets. And because of these slight deviations and getting the precise agreement, you now have an actual ordering of the sizes of the spheres. The moon is on the innermost sphere, then Mercury, Venus, the sun, Mars, Jupiter, Saturn, and then outside the celestial sphere of the fixed stars. And an example of how this process works out would be the planet Venus. Venus is a planet that, as we observe it in the sky, is never very far from the sun. It's sometimes a little bit west of the sun, and then it's a little bit ahead of the sun, and so we see it rising just before sunrise. Sometimes it's to the east of the sun, then we see it in the west in the evening sky, so then it's the evening star or the morning star. The way that's arranged in a Ptolemaic model is that the different for Venus moves at about the same rate as the sun does. In other words, the different orbits the Earth once a year, and then the epicycle rotation around that, which is not too large, accounts for the periodic change in elongation. In other words, the distance in right ascension between the sun and the planet. And Ptolemy builds in tilts, and the model, as I said, is somewhat elaborate. But at the end of the day, it's a successful mathematical model. And the reason I'm bringing this up is because it's often presented as the wrong model. It is not the way we think today, but it is certainly a wonderfully successful mathematical model of how things work. What was its competition? Well, from early on, there was an idea first attributed definitively to Aristarchus as early as 270 BC, which is that the perceived motion of the planets along the celestial sphere follows from the fact that both the planets and the Earth orbit the sun, and what we see is basically the result of the relative motion of the planets and the Earth. In other words, the solar system is now looking kind of like a racetrack along which the planets race. One of the principles of this model is that the planets closer to the sun move around the sun, orbit the sun in shorter periods, faster, and so the inside lane always wins. And as a result, when one planet is passing the other, you get the same effect when you're looking at the planet that you get when you're looking out the window of your car and it looks like, relative to the distant mountains, the trees near the road are moving backwards. The trees are not going anywhere, it's just that your line of sight is changing. We'll see that in a second. So this has a nice simple explanation for retrograde motion. Fine. The model that Aristarchus proposed was primitive, it needed elaboration, and nobody paid it enough attention to bring it up to the level of sophistication that it needed until Copernicus in the 16th century brings out a heliocentric model that is as detailed and as predictive and as successful as the Ptolemaic model. And the planets move along circles, and they move at uniform speed, and the way that this explains the non-uniform motion along the sky is because of this aspect of relative motion. We can do a nice calculation that might help us get a handle on this racetrack story. So imagine that we have planets and they're all orbiting the sun. Take some planet and let P for period be the time it takes that planet to complete one circuit around the sun. Because it's one complete circuit relative to the stars, we'll call it a sidereal period. Earth itself is a planet. It has its own period. We'll distinguish that with the name E for Earth's period. That is exactly the sidereal year that we discussed, the time it takes Earth to orbit the sun once with respect to the stars. Now, as with the moon, we'll define a synodic period, which we'll call S, which is the time between consecutive occurrences of some particular alignment between the Earth, the planet in question, and the sun, just as with the lunar phases. And we're going to try to relate these mathematically, something we sort of did for the moon, but it'll be instructive to do it here using this racetrack model. This is another one of those wonderful animations from the University of Nebraska-Lincoln. It's a very elaborate animation. You can do lots of things with it. I'm going to do something very simple. I want to understand the relation between synodic and sidereal periods. So what do we have here? Well, we have two planets. We have a blue planet, that's this one, and I'm going to assume that it has a sidereal period P1. That means P1 is the time it takes the blue planet to do a 360-degree circumlocution of the sun. I have another planet, I will call it the green planet, or number 2, because I do not have a working gray marker, and this one takes a period P2 to circumnavigate the sun, to complete a full sidereal orbit of 360 degrees around the sun in right ascension. And because of our assumptions, P1 being the inner planet takes a shorter time to go around the sun, so P1 is less than P2. Okay, suppose that I know these, or they are what they are. What I want to know is the following thing. I'm going to understand the synodic period. So what's the synodic period? That's the time between repeated alignments of the two planets and the sun. So for example, I am starting my animation right here very nicely in a situation where the three bodies are aligned. They're in a line. The synodic period will be the time that needs to pass before this pattern is repeated. And to see how long that takes, all we need to do is set the runners off and let them go. So I'm going to press the button and they're off and running. Let me stop and see what's going on. We were right. The blue planet is much faster than the green planet and is outrunning it. And as I let them run, indeed, within a short time, the blue planet is back home. What does that mean? Well, this means the time that we just watched was precisely this period P1. The blue planet completed a 360-degree sidereal rotation. Of course, the green one is nowhere near home. To keep track of what has gone on, let me give these guys trails. Imagine they were trailing smoke or something. This is what the blue planet has done so far, and this is what the green planet's done so far. But we're not back, as usual, we're not back to alignment, because in the time that it took the blue planet to get back where he was, the green planet has run away, and as we're by now familiar, to reproduce the synodic alignment, we need to keep going until, boom, there we go. Notice, we're back in alignment. So this, the time that passed until this happened, from here to here, is the synodic period. How do we compute it? Well, let's finish our star trails here. So this is a very ugly trail, but this is how far the green planet has gone. And this is how far the blue planet has gone, a full circle. And then, and then the same amount. Why? Because they started in the same place, they ended in the same place, but the blue planet has done an extra lap. This has taken a period S. Well, how much of a circle is this little arc? We've played that game before. This little arc, I will write it in green. The green arc is simply the fraction that S is out of the period P2. Because a time S has passed, and it takes a longer time, P2, for the green planet to complete a full circumlocution of the sun. Now, because they started at the same place and ended at the same place, one could be confused and imagine that this is the same as the fraction of a circle that the blue planet has done, because after all, it is the same fraction. However, the blue planet has gone through this arc, but also a complete circle. So in fact, this number is much bigger than this number. By how much? By a full circle. In other words, this, how much the green planet has done, is how much the blue planet has done, minus 1. And that is the equation we wanted. The three variables, synodic period, time between alignments, sidereal periods for the two planets, are related by this relation, and then if you know any two of them, you can get the third. Hooray! The actual resolution of the question, which of these two models describes the universe, was going to have to wait for better observations with a new technology that would definitively settle the question. Along the way, understanding how the heliocentric model, it will turn out, works out, led to insights that are much deeper than anything we've been discussing now, and far more broad in their implications than just understanding the stars. And it is following that trail that is going to occupy us for the rest of this week.